Okay. Good day, everyone. This is Yuki, Chen, and Linan from 360 Vulkan team. We come from China, and this is first time to London, and we are very excited. And thanks to for Vulkan committee to give us this opportunity. As mentioned, we come from China, and now this is 2 o'clock a.m. in China, so we just feel sleep now, and it's 7:30 a.m. p.m. here, so we also feel hungry. So in next 40 minutes, you are going to listen to sleepy and hungry man talking about exploit Internet Explorer. Early this year, we attended the Pwn2Own contest in. Sorry. Early this year, we attended the Pwn2Own contest in Vancouver, and this year's Pwn2Own has a lot of rule changes, which makes the contest more difficult. For example, this is first year that 64-bit Internet Explorer is used as a target, and exploiting 64-bit IE is much more difficult than 32-bit IE. For example, the heap spread technique cannot be used in 64-bit IE anymore. And this year's contest also enables enhanced protected mode sandbox for IE, which means the IE child process runs in the app container sandbox, and it has almost no access to most of the system resource. As the CEO of Open had some comments on this year's Pwn2Own contest, he said, Pwn2Own 2015 is a joke. It reduced the prices but raised the difficulties. So let's wait for next year. By the way, this year's price for IE is 65,000, and last year the price was 100,000. It actually reduced a lot in price, but raises a lot of difficulties. But we do not want to wait until next year, so we decided to accept this challenge. Fortunately, we succeeded, and today we'd like to share the details of the vulnerabilities and the exploit techniques we used in our Pwn2Own exploit. This is our agenda today. We used 2 bugs in our Pwn2Own exploit, so basically we have our agenda contains 2 parts. Part 1, we will introduce the first bug. This is an uninitialized memory bug, which we used to achieve remote code execution in IE child process. And the other one is a TOC/TOU bug, which we used to bypass the EPM sandbox of Internet Explorer. For each of the bugs, we will first introduce the detail of this bug, and then we will give the exploit techniques we used to exploit the bug. Here is a short self-introduction. We are from 360 Vulkan team. This is a Chinese security research team, and our company name is Qihu 316, which is the largest internet security company in China. We basically do security researches include zero-day hunting and APT research. And this is my colleague, Linan.
Hello, everybody. Hello.
Linan provides the first 0 day we used in the exploit. And he basically focused on vulnerability research. And my name is Yuki Chen. I'm a hardcore ACG otaku, and I love Japanese comics and animations. Okay, let's start today's topic. Let's introduce our first bug. This is an uninitialized memory bug. So what is an uninitialized memory bug? It is one category of memory corruption bugs. Uninitialized memory data is used in programs which were leading to unpredictable results. Here are 2 examples of uninitialized memory bugs. The first one, you can see we allocated an inter-array of 10 elements on the heap, and we access the first element of the array before initializing the array. This is a typical uninitialized heap memory bug. And the second example, you can see we have an inter-array on the stack. It has 10 elements, and we access to the first elements of this array before initializing it. And it is a typical uninitialized local variable bugs. Uninitialized memory bugs is common in program, and in history we have several nice and interesting uninitialized memory bugs, such as the IEMS XML bug, as demonstrated by Pwn2Own, and the flash uncompressed bug, which was exploited in the world last year. And this year we also have the Windows font driver bug by J00RU. When you successfully allocated a memory block, you own this memory block. But before you initialize this memory block, the memory block contains data which is left by the previous use, which is unpredictable. Access such uninitialized memory data is similar to that you get on a train and take a seat. And if there is a bag left by the previous passenger, then you cannot just access to this bag, or there will lead to unpredictable results. Our bug is caused by an uninitialized C attribute value in the C attribute array. We found this bug by fuzzing. As you know, DOM elements can contain attributes, and you can set attribute to DOM elements by calling the JavaScript function named setAttribute. And the C attribute value is the internal data structure used to store attributes in a DOM element. And about C attribute array, as its name indicates, it is the array to store all C attribute values in the DOM element. We need to go a little bit deep into the C attribute value for better understanding our exploiting process. Basically, C attribute value is a variant data type, which means it can contain different types of data. For example, an attribute value can contain int values or string or object or other data types. And the second byte in the C attribute value is important. It indicates the data type of this attribute. For example, if this byte is 8, which stands for VT BSTR, then this attribute will be a BSTR string attribute. Here is an example. We create a div element and set an attribute named AAA to this element. And if we look into the memory of this div element, we can see this div element contains a pointer to the C attribute arrays. And in the C attribute array, it contains an array to the C attribute values. And if we dump the first attribute value in the array, we can see it is exactly the one we just set in the, using the JavaScript. This type of this object is 8, which indicates it's a string, and it contains a pointer to the string data. This is a simplified POC of our bug. You can see it's very simple. We have two elements here. One is, the first one is the 8th elements of the DOM tree, and the other is a body element. And first, we set some attributes to the two elements, and then we merge the two elements by calling the merge attributes API. The merge attributes API will merge all attributes in both of the two elements and create a new attribute array which holds the result of the merge. So the bug exists in the implementation of the merge attributes API. You can see in our POC, the new created attribute array has 9 attributes. And the 4th attribute in this array is just skipped during the merge process and left uninitialized. It gives us an uninitialized C attribute value, which we can access from the JavaScript. Exploring this bug is a little bit complicated. We need several steps to do this. First, we need to use an information leak to leak some object address in the memory. And next, we need to create a fake C attribute to read arbitrary memory. And then we will create a fake JavaScript array with large length to achieve arbitrary read and write. And then we set up our shellcode and bypass control flow guard and EMET to execute our shellcode. We will explain each step in detail. The first thing first, to exploit an uninitialized memory bug, you need to be able to control the data of the uninitialized memory. And how? You can see we first allocated a memory block called B1 and fill it with our desired data. And next, we free B1. Note that although we freed the memory block of B1, the content of this memory block still remains in memory, which means we have a free block with which contains the data we need. And then we trigger our bug, and our uninitialized memory block will be allocated. And we will let it to reuse the free block that we just freed in step 2. And at this time, if you access the uninitialized part of this block, we are actually accessing the data left by the previously freed block. So we can control the uninitialized data. There are some key points to control. First, obviously, B1 and B2 should be allocated in the same heap. And next, the content of B1 should not be cleared after B1 is freed. This is based on the implementation of this object. There are some objects that will be zeroed out after they are freed. Then we cannot use these objects. And the third, the content of B2 should not be zeroed out when after we allocated B2. So if you use the API such as cmalloc or heapalloc with zero memory flag set, then we were not able to control the uninitialized memory. And back to our bug, since C attribute array is allocated with heapalloc without the zero memory flag set, so we are able to control the content of it. Now we have an uninitialized C attribute value, and we can control the content of it. Next question is, what data we will use to fill in the C attribute value? Our plan is to use some pointer type attributes such as string or object so that we can do something interesting with this attribute, such as leak some memory data or to control the execution flow. To do this, we need to know address which points to the memory to and inserting 2-bit Internet Explorer, it's easy to do this. We just use a heap spray and set this pointer to some address within our sprayed memory, such as 0x, 0c, 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 and then we can control this. But in 64-bit process, we cannot simply use a heap spring to do so. As you can see, in 64-bit Internet Explorer on Windows 8.1, the user mode heap use 14 bits as heap address, and that means assume a successful heap spring on 32-bit needs 200 megabytes. Then on 64-bit, you may need to spray probably more than 50 gigabytes. That's impossible in modern PC, yeah, in a normal PC. So yeah, simple spray of heap spray in 64 bits just does not work. So we need some kind of information leak here. Basically, to do information leak on 64-bit process, if you have a good enough bug, you may directly leak some address of interested objects such as string or JavaScript array. But usually, you will not have such a nice bug, and the common process is to first leak some objects within the same heap, and combined with some kind of heap function, you can guess the address of our interested data. This is how we do information leak use our bug. First, we allocate some attribute arrays, and each attribute array has 9 attributes. This number is the same as the uninitialized attribute array. And we set the fourth attribute in the array to a string of 0x30 bytes, as you can see here. And next, we free half of the C attribute arrays. And although the attribute arrays are freed, the content of the arrays will not be cleared. So it will look like this. We have some free block and contains the pointer to the string of 30 bytes. And next, we trigger our bug, and the uninitialized attribute array will be allocated. And if we are lucky enough, it will reuse the memory of one of the previously freed attribute array. So at this point, if we access the uninitialized attribute here, actually we can get a string attribute which points to the 0x30 bytes string that we allocated before. And next, we free the string object and allocate some runtime style objects, which is the same size with the string object. So the runtime style object will reuse the memory of the string object. But at this time, if we access the uninitialized C attribute here, it still thinks this is a string attribute. So we can read out the content of the runtime style object as a string. This leaks the contents of the C runtime object. And the first member of the runtime object is attribute array. which holds the runtime styles of a DOM element. So we can leak the address of this runtime style array. And now we have leaked the address of the attribute array. We will allocate many JavaScript arrays. Each JavaScript array is 0x1000 in size. And these JavaScript arrays will be allocated right after the runtime attribute array we just allocated before. So by adding the fixed offset to the address of the runtime attribute array, we can guess the address of one of the JavaScript arrays. This means we have address of a JavaScript array in memory, and we can set any data in the JavaScript array. So we can control the data content in a certain address. And this is very powerful. With this, we can make fake C attributes and continue our exploit process. To make a fake C attribute value, we need to trigger our bug for the second time. This time, we use JavaScript string to control the content of the uninitialized C attribute value. First, we allocate some JavaScript strings, and we fill the string with the content we want. And next, we free the strings. And then we trigger our bug. And this time, the uninitialized C attribute value will be controlled by the string data. So we can set the C attribute value to have any content we want. So we set up the attribute like this. We set the type of this attribute to be 0x0c, which means VT variant. So this attribute will point to a variant data structure. And we let this pointer to points into the int array whose address we just leaked. So this attribute now becomes a variant attribute. And the variant data points into the JavaScript array, which we can control. So we have full control of a variant data structure. If you do COM programming, you may be familiar with variant data structure. It is widely used in Windows, especially in COM interfaces. The variant is a data structure that can represent various types of data, such as int, long, or int ptr, or array object, or other object types. Since we have full control of this variant data structure, we can make it to any type of variant. And we can set it to a pointer to an assigned int. Using this, we can achieve arbitrary memory read. We set the type of this variant to a pointer to an unsigned int, and when this variant is an unsigned int, it contains a pointer into the memory, which points to the unsigned int data. So if we read this attribute out, we can read 4 bytes from the memory, which is pointed by the pointer. And we can set this pointer to be any address, which means we can read 4 bytes from anywhere in the memory. This is arbitrary memory read. And after this, we want to achieve arbitrary memory write. In IE exploit, usually we can corrupt the length field of a JavaScript array to achieve arbitrary memory write. But our bug is a bit different. Because we can make any type of variant data structure, then of course we can let it to be a fake JavaScript array object, which means we can create a JavaScript array of our own, and we can let its length to be very large. using this large JavaScript array, we can do arbitrary memory read and write. So this time we set the type of this variant to be the dispatch object. So it contains a pointer to the object, which is a fake JavaScript array. And we find a real JavaScript array and copy the contents of this real JavaScript array to our fake JavaScript array. After the copy, our fake JavaScript array will contain exactly the same data with real JavaScript array. So JavaScript engine will believe that this is really a JavaScript array object, except that we set the length of our fake JavaScript array to a very large value. Now we achieved arbitrary memory read and write in IE process. So next thing we want to do is to set up our shellcode and bypass the control flow guard and the EMET and execute our shellcode. If you have arbitrary memory read-write, this is not a big problem. The easiest way to do this is to hijack a valid core, which we can control the parameter of the core. And we can call some API such as virtual protect to set our shellcode to be executable. And then we can find a call which is not guarded by control flow guard and use this call to jump to our shellcode. Here we listed some methods to bypass the control flow guard, and you may choose the one that fits your bug. Now we have achieved remote code execution in the IE child process, but as you can see, it still runs in app container, which means it is still protected by the EPM sandbox, and it has almost has no access to most of the system resources. So next task is to bypass this, bypass the EPM sandbox and execute our payload, at least in medium integrity level. So this is the second bug we used in the exploit. This is, we use it to bypass the EPM sandbox. Enhanced product mode is a security feature that was introduced in Windows 8. And by default, Internet Explorer 11 does not enable the enhanced product mode. And James Forshaw has very nice introduction and very good examples on how to bypass EPM sandbox. When EPM sandbox is enabled, IE child process will run in app container. And app container is a new process isolation mechanism introduced in Windows 8.1. It offers more fine-grained security permissions, which blocks most read and write access to most of the system resources. For example, the IE child process even has no access to the system temp folder because it is protected by EPM sandbox. And the bug we use to bypass this sandbox is a time of check to time of use bug, or sometimes also called a race condition bug. This bug exists in the IE install service broker. As we mentioned before, app container process can only access to very limited system resources, but sometimes these processes still need to access some resources to provide their normal functionality. And there are some medium integrity level processes which provide such access to the app container processes. These processes are called the broker services. And the IE install service broker is one of these broker services. It is used to install components in Internet Explorer, such as add-ons. The executable file of this broker service is ieinstall.exe, which is under the IE program folder. We can use this broker service to install components, and it is accessible from the app container process. To install a component using IE install service broker, basically we need 3 steps. First, we obtain an interface of this install object, and then we call verifier file, install file, and register exe file one by one. If either of the 3 calls fails, the installation will be failed. The first call is called verify file. This is the most important step from the perspective of security. It will check that whether the file you want to install has valid signature. If the file does not contain a valid signature, the install will be failed. It also checks that whether your file is from a low integrity level folder. If so, the installation will be failed also. And the second step is called install file. It simply copies the file to the destination folder where we want to install this component. And the third step, called register exe file, in this step, it will execute the file to be installed by calling the create process API. And it seems we cannot install unsigned program using this broker. But if you look at the 3 steps carefully, you can find that there is a problem in the 3 steps process. The problem is it verifies the file in the first step, and it executes the file in the third step. But before it executes this program in the third step, it does not verify the file again. So it cannot guarantee that the file verified in the first step and the file executed in the third step are the same one. So we can exploit this bug like this. First, we call verify file to verify the iExplorer.exe, which is the executable file of Internet Explorer. And of course, the verify step can be passed because it contains valid signature from Microsoft. And then we call install file, and iExplorer will be copied to our destination folder. And next, the most important step here, before we call the third step, we replace the iExplorer. We replace the iExplorer executable in the destination folder with our program. For example, we can rename a calculator to iExplorer and copy it to the destination folder to overwrite the original one. And then we call register exe file in the third step, and by doing this, our process will be executed by the broker service, and it will run in media integrity level, which means we bypass the EPM sandbox. It sounds like it seems to be a nice plan, but we have another problem here. The destination folder of the installation should have at least media integrity level. because our program is started from this folder. And if this folder is low integrity, the process started in this folder will also be low integrity. In that case, we will not be able to bypass the EPM sandbox. And because we need to replace the file in the destination folder, we must have the write access to that folder. So it means we must have write access to a median integrity level folder. But as mentioned before, the APP container process has very limited access to these folders. It cannot write to the median integrity level folder by default. So we need to find a median integrity level folder that we can write to from the IE APP container process. And we find some way to do this. We can use Flash Broker to achieve this. Flash Broker is a broker service for Flash Player add-ons. Because Flash Player runs in IE EPM sandbox, it also needs some some access to the, for example, the Adobe Flash folder. So Flash Broker provides the interface to read and write files to some predefined locations. And one of the locations here, as you can see, the APP data roaming and Adobe folder under the user folder is a median integrity level folder. And we can write to this folder from the IE EPM process using the Flash Broker. Here is a little problem here. The Flash Broker has a wide list of file extensions, and you can only create file with extensions in this whitelist. And the exe file is not in this whitelist. So we cannot create a file with extension of exe using the Flash Broker. But that's not a big problem because create process will automatically check the PE file for us. So we can just drop a PE file named say 1.top or 1.jpg or whatever. And we create a process on this file, and it will correctly execute this file as a PE file. And Flash Broker has another defense line against writing PE files. In the Flash Broker API named the broker write file, it will check whether you are going to write a PE file by checking the DOS signature and PE signature in the buffer you want to write. If it finds such signature, it will deny the write request. But it only checks the signature at the first time when you write to the beginning of the file. So we can bypass this defense like this. First, we write the beginning of the file without the DOS signature. We can simply replace the DOS signature with 0 bytes, so it can bypass the check. And later, we use the broker set file pointer to set our file pointer back to the beginning of the file. And this time, we write the DOS signature. And by doing this, we have a complete PE file. So this is obviously a security bug in Adobe Flash Player. And combine all of this together, we are finally able to execute median integrity level calculator in, and we finished the contest finally. So this is our content today. And we'd like to thank for Volcan committee for giving us this opportunity here. And also thanks to the guys in 316 Volcan team for working out the exploit together. And we are looking for security researchers. And if you are interested in working in China, you can drop us a mail. Yeah. And we're glad. So